Okay, this is 11.3, Electric Interactions and Conservation of Energy. First of all, the law of conservation of energy states that energy cannot be created nor destroyed. I should put cannot be. Cannot be created nor destroyed. Okay, now in formula form, we typically talk about this as being the potential energy plus the kinetic energy before some interaction takes place is equal to the potential energy after and the kinetic energy after. But when we take a look at what's happening within an electric field, sometimes where things are change a little bit. So if we were to have, let's say, and that looks just awful. Let's draw one line here and another line here. So we've got two positive plates. Okay, two positive plates, or two plates. We'll call this side negative and this side positive. And there's an electric field that is going on between these two plates, right? And the electric field is going this way, the way a positive test charge would move within this field. Now, if we had a positive charge here, it would have high potential energy. And as it moved with the electric field, because it would be repelled by the positive, attracted to the negative, it would lose that potential energy and gain kinetic energy. So it's going from potential to kinetic energy this way. However, even though the field is going to the left in this video, if we had a negative charge here, this is where that negative charge would have high potential energy, and as it moved along this way, it would be transferred to kinetic energy, and that would be by a force that would be acting upon either the positive or negative charge that would be equal to the electric field strength multiplied by the charge. Now, the potential energy in either case is going to be equal to the voltage multiplied by the charge, right? Or the voltage or electric potential difference. And the kinetic energy, as regularly done, is 1/2 mv squared. And then we can use them to calculate. Notice that this formula here is not on your formula sheet, but it does explain the concept. This can be very helpful for us solving for many, many problems. Let's take a look at our first example here. Okay, we've got a negative charge of 3 times 10 to the negative 9 coulombs at rest in electric field and has a 3.2 times 10 to the 19 joules of potential energy. Right? So what we've got is here, and I know my horizontal lines are not very good. It's a negative charge here with a charge of 3 times 10 to the negative 9 coulombs. And it's going to be here. At this point here, we're told it has a potential energy of 3.2 times 10 to the negative 12 joules. Okay, and so what we're asked, when released, the negative charge accelerates towards the positive charge. What is the kinetic energy just before striking the positive, I should say plate, but heading over here. So as it is here, what is the kinetic energy? Okay. So taking a look at the standard law of conservation of energy formula, The potential energy we know is 3.2 times 10 to the negative 12 joules. It is at rest at this position, therefore it has no kinetic energy. And just before it hits the plate, it will have no electric potential at that point. And we're just looking for the EK after, which means really the answer is just 3.2 times 10 to the negative 12 joules as the kinetic energy it'll have afterwards, because all that energy is transformed to kinetic. Okay, give this next one a try. Okay, pause the video, give it a try, and afterwards unpause the video, see how you do. Okay, you should have found that you had an answer of 2.3 times 10 to the 6 joules. What's happening here again is we've got a positive charge. We want to know how much potential energy it has here. As it zooms along, it has 5.2 times 10 to the 4 meters per second of velocity. And we know that the mass here is 1.7 times 10 to the negative 3 kilograms, and it's accelerating towards this positive charge, which means that the kinetic energy after will be equal to the potential energy it had before, again, assuming it started from rest, which we are told right here that it started from rest. Okay, let's take a look at example number 2 now. We've got an alpha particle placed between two charged plates. So we've got the two plates, we've got the alpha particle sitting right here. There is 40,000, 4 times 10 to the 4 volts between these two plates. And what we're looking for is the speed at which this is going to strike the negative plate after it zooms along. It initially started at rest, 0 meters per second, and is zooming along this way. Okay. We don't know the distance between the plates, but we should be able to work around without that. But we start off with potential energy and no kinetic energy, becoming no potential energy and all kinetic energy. This potential energy is the voltage divided by the charge. Now, the potential difference between the plates, it's that full 40,000, so we don't need to worry about, we can use a full 40,000 here. It's equal to 1/2 mv squared. We are looking for the speed, we're looking for that velocity there. So 2vq, multiplying both sides by 2, dividing by mass, and square rooting will get you the velocity. So 2 times the voltage, that 4 times 10 to the 4. The charge, it's an alpha particle, 3.2 times 10 to the negative 19 coulombs, divided by the mass of an alpha particle, which we know is 6.65 times 10 to the negative 27 kilograms, is equal to V, because we've all square rooted that. And so your answer here is 1.96 times 10 to the 6 meters per second is equal to the velocity. Oh wait, we want the direction. No direction, just speed, so it's just the speed, no vector. Okay, again, pause the video, give this next one a try. Let me know how you do. Okay, in this case here, we got a charge of 6 times 10 to the negative 6 coulombs. It's gaining 3.2 times 10 to the negative 4 joules of kinetic energy as it accelerates between the plates. Now, we don't know for sure if the kinetic energy started at 0 and the potential energy ended at 0. However, if we started with some kinetic energy, we'd just be adding it to this side anyway, and so using 0 seems to be the easiest. We've been given that total change in energy multiplied by the 0.6, divided by the 6 times 10 to the negative 6 gets you the 53.3 volts of electric potential difference. Now, our formula sheets, on the Alberta government formula sheets, it is written where a change in potential energy is equal to the change in energy overall divided by Q. And we see that we've essentially done the same thing here as what we had on this formula sheet, but it starts from this point. And so we can jump straight to this in many incidences where we're dealing with just a change in energy overall. Usually looking at the kinetic energy, although it does work with a change in potential energy as well. Okay, taking a look at the third example, we've got two horizontal plates. We know that they're 1.2 times 10 to the negative 2 meters apart. But we're not really worried about that so much, because as this comes along, it's going to bend towards the negative plate away from the positive plate. The electric field is, again, the way the positive test charge would move, and this positive charge would move towards the negative plate. What we want to know is really how far does it move towards this plate. We're looking for this d. The distance between them is not really relevant, assuming it's not actually hitting the plate. So what we're looking at here is, in fact, essentially a horizontal projectile question. It looks a little funny because it's falling upwards from our perspective, but that's essentially what it's doing. Now, in this case here, this force that it's going to be experiencing up, this F, which is normally equal to ma, which means that the force divided by mass would get us that acceleration. That force is the electric field multiplied by the charge divided by the mass will get us the acceleration. Now, we are told a couple of things. First of all, the electric field is 1.7 times 10 to the 5 volts per meter. We're told the charge on this positive sphere is 2.6 times 10 to the negative 12. And we're also told the mass of the sphere. And so these three numbers that are highlighted are going to be used to calculate the acceleration, which is 1.47 times 10 to the 8 meters per second squared up. Now that we've got that, we know the time that this is moving in that direction is 6 times 10 to the negative 6 seconds. Right? So because we've got the time of 6 times 10 to the negative 6 seconds, we have the acceleration of 1.47 times 10 to the 8 meters per second squared. We know the initial velocity is 0 in the y direction, and we're looking for the displacement in the y direction. Essentially, we're doing this, but we only need stuff from the y direction because we have found that acceleration and we've been given time. So using d is equal to VIT plus 1/2 AT squared, that displacement, VIT cancels out, 1/2 AT squared is 2.7 times 10 to the negative 3 meters per second. Or meters, not meters per second, just meters. All right. Okay, give this next one a try. Pause the video, let me know how you do. Okay, so the electron is moving towards the positive plate. We want to know how long it takes, so we're looking for a distance that it's traveling, time that it's traveling 1 times 10 to the negative 2 meters in that vertical direction. Finding the acceleration, as we did before, using electric field strength and the charge and the mass of the electron, will get us 2.63 times 10 to the 13 meters per second squared. So we've got initial velocity 0 because it's moving horizontally. So VIT can be crossed off. Is equal to 1/2 AT squared. Manipulate to isolate for t, which will be root 2d over a. And we're going to plug in our numbers and solve for 2.7 times 10 to the negative 8. Hope this helps, and thanks for watching.